Okay, so what we have seen in this model, we have seen that our two variables such as ex and cons are co-integrated. So now we can run the error correction model. Okay, now we shall develop the error correction model. So how to develop, how to write error correction model. So mm, so uh, so error correction model is something like this. I go to quick, then I go to estimate equation. Okay, error correction model should be, the data should be in first difference. You see, ex, I write it dex. That means it is the first difference, meaning that ex becomes stationary because the data, because the variable has already converted to first difference. Then I write C, which is intercept of the regression model. Then I put our next variable, which is cons. What is cons? Cons is the independent variable. And what is decons? Decons is the first difference of cons variable, meaning that cons has become stationary after first difference. And then I draw the error correction model, error correction term. What is that? That is u minus 1. What does it mean? U minus 1 means 1 period lag of the residual. Last time, can you remember? Last time we developed this u, right? Last time we created the u. What is the u? U is the residual of the regression model, such as this one, the residual of this regression model, that is u, and 1 period lag. So when I do it, this one is called error correction model. So I'm telling again, here ex is the dependent variable and cons is the independent variable, and 1 period lag of the residual is also another variable, and this one is called error correction model. And u, 1 period lag, is called error correction term. And what is u? Residual of this model that we have estimated already, right? Okay, now we can run this error correction model and see what happens. Okay, and you see this one is called ECM, error correction model, because here is only single equation. It is not VECM. What is VECM? VECM is vector error correction model, which should have a number of equations that can be solved at a time. But here, in case of ECM, it is only one equation, one-way causation. That is why it is ECM, not VECM. And here I have used only one independent variable, but if you want, you can use a number of independent variables, right? That you can do. However, I run the model. Okay, so this is the outcome of the model. You see from here. So dEx is the first difference of Ex, and it has become stationary. So, and C is the constant, dcons is the first difference of cons, which has become stationary. We assume that last time I said that first difference of Ex and cons is stationary, right? And in the time series data, we should use the stationary variable, and it is the error correction term, one period lag of the residual from the previous regression model. Okay, here dcons is what? This coefficient is not long run coefficient. 0.41 is a short run coefficient. And is it significant? No, because the p-value is 59.96%. The p-value is 59.96%, which is more than 5%. So short run coefficient, that is dcons, is not a significant variable to explain our dependent variable, which is Ex. So that is a bad sign. Then what about error correction term? How much is this one? 20.69%. 20.69%. It means that error correction term actually correct the disequilibrium of the system. I am telling again, error correction term actually correct the disequilibrium of the system. That is her task. That is her job. Okay, here the speed at which she is correcting disequilibrium is 20.69% annually. Here we have the annual data, right? The data we are using in this model is annual data. So error correction term, she is correcting the disequilibrium at the rate of 20.69% annually. Speed of adjustment is 20.69% annually, right? In other way, she is adjusting with the previous period disequilibrium at the rate of 20.69%. Or in other way, speed of adjustment of the disequilibrium is 20.69%. That is the meaning of the error correction term. But here there are two things is good. The sign is negative and it is significant because the p-value is 1.34%, which is less than 5%. And when the p-value is less than 5%, then that particular variable becomes significant. So here error correction term is a significant. Okay, it has negative sign and also it is significant. It means that our EX and cons, our it is giving validity when you lag one residual is significant and negative sign, it gives the validity that EX and cons have a long run equilibrium relationship, because error correction term is negative and significant. So it gives the validity that EX and cons have long run relationship. Okay. And finally, is this model is spurious? Spurious. So what is the guideline of spurious? The guideline of spurious is R square value should be greater than Durbin-Watson statistics. But here you can see R square value is smaller than Durbin-Watson statistics, meaning that our error correction model is not a spurious model, or our error correction model is not a nonsense model. We can accept the model. All right. Okay, now what do you want to check further? Suppose we want to check whether this error correction model has a serial correlation or not. That you want to check, right? Whether the residuals are serially correlated or not. That we want to check, right? How to check? I go to view, I go to residual diagnostic, I go to serial correlation LM test, right? So I click here, and here is already 2 lag. Okay, I take it 2 lag, then I okay. So it is the Bush-Godfrey serial correlation test, and normally we choose observed R square and corresponding p-value. What is the p-value? P-value is less than 5%, meaning that we reject null hypothesis and accept alternative hypothesis. And what is our alternative hypothesis? Alternative hypothesis is that model is serially correlated, or our error correction model is serially correlated, or the residual of the error correction model is serially correlated. So meaning that our error correction model has a problem. What is the problem? The model is suffering from serial correlation, which is not desirable. Okay, then we check whether the residual is normally distributed or not. I check the normal distribution, go to view, residual test, then test of normality. I click here. The result has come up. The Jarkabera statistics and the p-value, right? You can see from here, Jarkabera and p-value. What is the p-value? P-value is less than 5%. So meaning that we can reject null hypothesis and accept alternative. What is our alternative hypothesis? Alternative hypothesis is the residual is not normal. The residual of the error correction model is not normally distributed, but that is not desirable. What is the desirable? Residual should be normally distributed. That is desirable. But here in our error correction model, residual is not normally distributed. So here we have two problems. One problem, error correction model is suffering from serial correlation, and second problem is that the residual is not normally distributed, which is not desirable. So these are the bad side of our error correction model. So these are the bad sides. So we have to design our model, our error correction model, in a such a way so that these two problems cannot come up. Right? We have to do something. We have to do something so that serial correlation or not normal residual do not come up. We have to do that. So that is the end of the story, and yeah. So here I have just shown ECM, but in other place I have shown the VECM, right? In our other place, may not be here. Okay, what I'm showing here, I'm telling the whole story one by one, that I already just am giving the whole things at a time. You can see from here, right? Just I start from here. Okay, so the whole model, the whole story that I said previously. Okay, I just adjust it first a little bit, then I come back to you. Okay, adjust slightly. Okay, here I am taking the whole picture that I said today. Is coming up gradually, right?